So we can continue.
Yes, we can continue.
Okay. So we have something to discuss, and then we turn to this problem with two sequences. Okay?
Okay.
Okay.
Okay. So page 55. Here we have the definition of the so-called Cauchy sequence. You see, it is an important tool in the mathematical analysis. So if I have a Cauchy sequence, then I can say that this sequence converges. And if the sequence converges, then it is a Cauchy sequence. So if and only if it is a theorem, I hope you know this from your lectures. Now, we try to read this definition. So a sequence of real numbers is called Cauchy sequence if for any epsilon strictly positive there exists a positive integer k, capital K, which depends on epsilon, as in the definition of the limit, such that for any m n greater than k, we have that the absolute value of m, a sub m and a sub n is less than epsilon. You see, it is rather near uh, from the definition of the limit. If you imagine a real axis and you have some point A, which is the limit of a sequence A sub n, you see that for an epsilon, you can find a number such that all the terms of your sequence are in some neighborhood of this point A. You know this.
Yes, we know.
Not only not only in terms of inequalities, because the inequality it is the same thing as the neighborhood of this point. You see, in this case, what we want to say, if for this epsilon fixed, I take two numbers of m and n, so I take two terms of my sequence. These terms are in this neighborhood of my limit. So they are very close, in fact, in terms say that the absolute value of the difference of these terms is small. Is it clear or not? Or I have to explain better?
It's like the sequence conversion.
Yes, it's a convergent sequence, but you see, Valentina, in this case, if we discuss only the limit, as for the limit, I say I take some epsilon, then beginning from 1, from some capital K, from some capital K cut off number, which depends on epsilon, all the terms of my sequence are in the neighborhood, in the epsilon neighborhood of your limit. In the case of Cauchy sequence of this definition, you see, we do not say that there exists a limit or something else, but we say that beginning from this cut-off number, capital K, all the terms of our sequence are very close, such that the absolute value of an and am, the difference, is less than epsilon. Is it clear? So it's in some way it is the same thing, because we are always in some neighborhood of our limit, but here we do not precise the limit, but all the terms of my sequence are somewhere in a small neighborhood of something which will be the limit in the theorem which claims that a Cauchy sequence converges.
Okay,
Is,
it's clear.
it is clear. So, Valentina, if you want, you take a pen, a sheet of paper, you try to write, not to plot, to give a picture. You have some point on a real axis and a neighborhood of this point, and we can suppose that it is a limit. But then there is no point, something like this, but you have all the terms of your sequence which are in this neighborhood. And if we take epsilon smaller and smaller, then the infinite number of the terms of my sequence are in this neighborhood. You see, if I take xn or xm or something else, I do not speak about the limit, but I have that all the terms of my sequence are in a small neighborhood of something, which will be the limit, in fact. But they are very, very close.
For this is the sequence is not Cauchy, is like tends to infinity or minus infinity.
No, Valentina. You see, if your sequence is not Cauchy limit or is not Cauchy sequence, that it is not a convergent sequence. So it is. We will discuss this with this homework or the task for Eric. But you can. What do you know about the subsequences?
Yes, I know about that.
So you see, if you take this sequence, something like -1 to the power n, okay?
Yeah.
We take this sequence. So it will be a sequence like this. 1 -1 or -1 1 -1 1 -1 1 and so on. You see?
Yeah.
In fact, this sequence have two subsequences. The first one, a constant subsequence, -1, -1, -1, and so on. Second one is 1, 1, 1, and so on. You see, the first and the second are the sequence which converge. Yes?
Yeah.
The first one converges to -1, the second one converges to +1. In this case, you see, in this case, we can say, due to general theory, if a sequence have two subsequences which converge to different limits, then the whole sequence does not converge. Does
Okay.
not converge.
Yeah, I understand.
You see, it's an important result, but in
All
mathematics,
the subsequence need to converge to the same limit.
yes, exactly. But you see, from the other hand, it is something like a mathematical trick. We say that my sequence converges to plus or minus infinity. You see, in some way, this sequence is not convergent. It's not convergent because if you take a sequence 1, 2, 3, so on, and so on, this sequence is not convergent, it is not bounded, but we can say that the limit of this sequence is plus infinity. It is maybe it is not very good, but as for the second sequence, because in this case of 1, 2, and so on, n, any subsequence converges to plus infinity, yes?
Yes.
But in the case of -1 to the power n, you will have something like a convergence which has no limit, no infinity, no plus infinity, no minus infinity, but no limit. Here is the difference.
Yes, I got it.
So, for example, try to consider as a homework, Valentina, try to consider a sequence, sin, sinus of p pi over 2 multiplied by n.
Okay.
What can we have? And also, in order to compare, you can consider the sequence cosinus pi multiplied by n, and also sinus sinus of pi multiplied by n. You will have some interesting sequences in this case. You see?
Yes, but in this homework we need the two sequence
No,
apart
no, we will
tends to 0. Yeah?
listen. Now we will finish with our plan if you want, and then we will discuss this situation with two sequences xn and yn.
Okay.
Okay. Now you turn the page and you have an equivalent formulation of the Cauchy sequence. So you see, really, to my mind, the second definition is better because we can easily check it. Easily, not easily, but it is better to check. You see, in the second definition, we say that a sequence is a sequence of called Cauchy sequence if for any epsilon there exists a positive integer, our cutoff, capital K, which depends on epsilon, such that, you see, for any n greater than K and any natural P. You see, in the first definition, you have something like M and N greater than K. So we will see in the examples that it is better to work with the second version of this definition because it is better to check, to work with the absolute value of A sub n plus t minus A sub n. So now the second version is for any epsilon there exists K such that for any n greater than K and any P natural, we have that the absolute value of n plus P minus an is less than epsilon. Good. So the first and the simplest example here, we turn the page and we have a sequence which is the sequence x sub n 1 over n. We know that the limit of this sequence exists, but we can also check that this sequence is really a Cauchy sequence. So if I fix my epsilon strictly positive, then I want to consider the absolute value of xn minus x sub n plus t. So in this case, 1 over n minus 1 over n plus p. We do not need here the absolute value because 1 over n is greater than 1 over n plus p. Yes?
Yes,
Yeah.
it's clear.
Yes, it's clear. Then you have the difference of two positive numbers. Here you see the idea. In some way, I want to forget about P because in this definition, I say that we have the absolute value of x or an minus an plus p less than epsilon for any p natural. So if I can avoid, I say, this letter t, and I have only n, then I can say that beginning from some and everything is good, but it happens for raw T nature. So the idea is to reduce, I don't know how to say in this case, this T. In this case, it is very simple because we have the difference between 1 over n and 1 over n plus p, which is less than 1 over n. You see?
Yeah, it's clear.
It's clear. You see, now, what is important for this kind